Let me check. I don't know.
All right, let's get started. So I will try to remind you where we finished off yesterday. So we were trying to build a theory where the Goldstone bosons have the properties like the Higgs. Nevertheless, and there is a gauge standard model included there. Nevertheless, these Goldstone bosons don't get a one-loop quadratic divergence from the interactions with the gauge bosons. Yes, that was sort of our initial goal. Yes, so what we said is that the theory that eventually seems to be working, so that's the model that is called the simplest little Higgs. Yes, and of course, since it's the simplest, that's why I'm explaining this particular one first. And so here the idea was that you have an SU3 cross SU3 global symmetry. Each of these SU3s are broken spontaneously to SU2. Yes. So each of these produce a set of Goldstone bosons, a set of 5 Goldstone bosons. Yes. And then what we do is we gauge the diagonal subgroup of the SU3. Okay. And then the diagonal SU3 is gauged. Yes. So that means that when in this process of breaking the SU3s to SU2, yes, the SU3 gauge symmetry will also be broken to SU2 gauge. Yes. So in that process, 5 Goldstone bosons will be eaten. Yes. But we had 2 times 5 Goldstone bosons. Yes. So one set of those is going to remain as a physical set of Goldstone bosons. And those will have the right property to behave like the standard model Higgs. Okay, so we have these 2 nonlinear sigma model fields, e to the I pi 1 over f, 0, 0, f. Yes, and for simplicity, I took these 2 scales in the 2 breakings to be equal, e to the I pi 2 over f, 0, 0, f. Of course, you can make it more complicated. These 2 scales don't have to be exactly equal. There will be more, mixing angles in the formulae, but it's not important right now. Yes, and then one combination, the sum of these 2 Goldstone bosons is going to be eaten by the gauging of the diagonal SU3 at the gauging and then the breaking of the diagonal SU3 down to SU2. But one combination, the difference of these 2 is going to remain as a physical Goldstone boson. Okay, so that's very nice. And the most important aspect was that when I now start calculating what the one-loop quadratic divergence is, the piece of the Coleman-Weinberg potential coming from the gauge interactions of these SU3 gauge bosons with the Goldstones, yes, so you just go ahead and write out d mu phi 1 absolute value squared plus the mu phi 2 absolute value squared, just like we discussed yesterday. Yes, so the entire thing is gauged, and what you find is that this whole Coleman-Weinberg potential is going to be independent of the Goldstone bosons, at least the quadratically divergent part. Yes, the lambda squared over 16 pi squared times g squared, and then you will get here a phi 1 dagger phi 1 plus a phi 2 dagger phi 2. Yes, and the Goldstone bosons nicely drop out from here. Yes, so there's no quadratically divergent one-loop contribution to the Goldstone bosons. Okay, and pi 1 plus pi 2 is eaten, yes, as I mentioned, and pi 1 minus pi 2, so that's physical. And that is the one that can play the role of the Higgs. Yes.
So only SU2.
Sorry. Question over there. No. So the question was, do the 2 F's have to be the same? Yes. I sort of mentioned that before. Yes. I just took it the same for simplicity, so that the formulae, if it's not the same, yes, then it's not going to be just the sum and the difference, but it's going to be weighted by the two f's and then the square root of f1 squared plus f2 squared. Yes, you die. I'm sorry? No. So that's important, yes? If you only gauged the SU2 subgroup of... So the question was, is the whole SU3 gauged or SU2 subgroup? Yes. So we saw yesterday, if I tried to just gauge the SU2 subgroup of the SU3, yes, that's an explicit breaking, and that on its own will already give you quadratic divergences, yes. In that case, that was the case, you remember, when the Coleman-Weinberg potential looked something like this, yes, phi 1 dagger 1, 1, 0, phi 1, yes, and that one gave, that one did depend on the Higgs, yes. It was important that this turns out to be the unit matrix, yes, and that happens if you gauge the entire SU3 subgroup. Okay, and another way to see that it's got to be that, yes, because if you only gauge the SU2 diagonal, the SU2, yes, then you basically didn't add any new particles, yes, to the theory, yes. So there's nothing that would truly cut off the quadratic divergence of the standard model. You need some new particles, yes, and those will be these, new gauge bosons, the SU3 completion of the SU2, which will be doing the cutting of the standard model quadratic divergence. All right, very good. So, but the main question is, why? Yes, why does this? It's great that it doesn't depend on the goldstones, but why doesn't it? Right. So there are how many massive gauge bosons? Yes. So you started out with 8 gauge bosons. Yes. At this point, this is before electroweak symmetry breaking. Yes. When SU3 is broken to SU2, yes, each of this is going to break the SU3 down to SU2. We're assuming that these are aligned with each other, yes. So 5 massive gauge bosons and 3 massless gauge bosons, which are the W plus minus and the Z. Okay, so but we'll discuss that. All right, again, why? Yes. So that's sort of the most important concept, yes, which is the idea of collective symmetry breaking. So the important thing is that, so we have worked very hard to achieve the following thing, yes. We first produced a global symmetry, then we broke it spontaneously, that produced the goldstones, but that's not enough, yes, because in order for the goldstone to have properties like the Higgs, yes, we also have to break the symmetry explicitly. We know that, a true goldstone boson will not behave like the Higgs. It doesn't have non-derivative interactions, while the Higgs does. So we have to break the symmetry explicitly, yes. But then the worry is, as we saw in the previous lecture, that once you break it explicitly, you will reintroduce the quadratic divergences, yes. So the trick, what this model has achieved, was that you did the breaking, the explicit breaking, nevertheless you didn't reintroduce the one-loop quadratic divergences. And the reason for that is because the symmetry, the global symmetry, was actually collectively broken. And what this means is that actually there are now several interactions here that affect the Goldstone boson, yes. So the Goldstone boson, the true physical Goldstone boson, lives both in phi 1 and in phi 2, yes. And it has interactions with the SU3 gauge field from both of these terms, yes. So you have an interaction of the form GA1 times phi 1 absolute value squared plus GA2 times phi 2 absolute value squared. Yes. And the important thing is that if either of these two couplings is turned off, yes, then actually the global symmetry would not be broken. Yes. If either of these was absent, yes, then the SU3 cross SU3 global symmetry would not be broken. not be broken explicitly. Yes, of course, we have the spontaneous breaking. Yes, but there would be no explicit breaking. Yes, because let's say if this term is not there. Yes, then well, phi 1 has its own SU3 symmetry, and then here phi 2 has its own SU3 symmetry, which is gauged, and that's not a breaking of the SU3 symmetry. Yes, I could get rid of this. Yes, and I would have the same story with the other SU3. Yes, so only when both of these terms are present is the SU3 cross SU3 global symmetry truly explicitly broken. Okay, so why is this important? Yes, the reason why it's important is because in the absence of one of these couplings, there is no breaking. Hence, it means that any diagram that only includes one of these two terms cannot possibly depend on the Goldstone bosons. Yes, because any diagram that doesn't feel both couplings, yes, can be derived from a theory that still has the full global symmetry, where where these pions are true Goldstone bosons. So only diagrams that include both of these couplings will potentially be quadratically will depend on the Goldstone bosons. Yes, but then it means that I have to have more than one coupling showing up in these diagrams. Yes, so it means that those diagrams will actually be softer than you naively expect. Okay, so that's the key idea here. Okay, so diagrams with just one coupling, yes, for example, the first one, yes, will only depend on phi 1 dagger phi 1. We'll have the form phi 1 dagger phi 1, yes, if it's on the first coupling, or phi 2 dagger phi 2. Yes, and those will actually not depend. Those could be quadratically divergent. Yes, they just don't depend on the Goldstone. Okay, so we don't care about it. Yes, so the lowest diagram that depends on both of these. Yes, so the lowest that depends on the Goldstone it has to include both of these interaction vertices. Yes, so you can have one here. You have phi 1 dagger phi 1, and then here you have your gauge bosons. Yes, but if I just close it up without any other vertex, yes, then it depends only on phi 1. So I have to put in another interaction. Yes, and then I have to put in the one with the phi 2s. Yes, so that's the first one that has a chance of actually depending on the Goldstone bosons. Yes, but now you can see this is no longer quadratically divergent. Yes, so this is now you have two gauge boson propagators here. Yes, so this is only log divergent. Okay, so the leading expression for the mass parameter that is generated by loops in this case, yes, you'll have to have a form like this: phi 1 times phi 2 absolute value squared times g to the 4 over 16 pi squared times some log of the cutoff scale divided by some IR scale, whatever the IR scale of the theory is. Yes, so now this combination can depend on the Goldstones, yes, and it will depend on the Goldstones. This is out of this one, the Goldstone does not drop out, yes, because it's the difference of the two Goldstones that is the physical Goldstone. So the physical Goldstone does not drop out from here. So you can express this in terms of the physical Goldstone. So this is going to be f squared minus 2h dagger h, where h is the physical Higgs. There are eta pieces, I don't care about it. And so that means that your leading mass correction to this to the Higgs here, yes, will have this loop factor g to the 4 over 16 pi squared, yes, times an f squared times log lambda squared, so log divergent, times h dagger h. Okay, so this is going to be the correction, yes, of the Higgs mass parameter. Yes, so if this f is something of the order of 1 TeV, yes, then this is going to be nicely loop suppressed compared to that, and you can nicely push this down to around 100 GeV. Okay, so this is really the most important part. Yeah? So this is the idea of collective breaking. And another way to ask is, what this collecting breaking is about is to ask the question, so who really cancels the quadratic divergences of the standard model gauge bosons? Okay, so who does the cancellation? Yes, so basically what we are saying is that in the standard model, you have these diagrams where you have a W and a Z running in the loop. Yes, and then the question is, why is this not truly quadratically divergent? And the answer here is that, well, because I have these additional gauge bosons running in the loop. Yes, those additional gauge bosons are the ones that become massive when SU3 is broken down to SU2. Yes, so now we have more gauge bosons. Yes, so in addition to the W and the Z, this whole thing is extended to an octet of SU3. Yes, so you will have here the W plus, the W minus as usual, but then you will have here an X plus, an X minus, and then some Y's, whatever they are, doesn't matter, Y10 plus I times Y20. So these are two neutral gauge bosons, Y10 minus I, Y20. It doesn't quite matter. There are 8 of them, yes. And then there is the A3 and the A8. Yes, those are also distributed here along the diagonal. Yeah, so the important thing is that now you go ahead and try to calculate, what the full interaction between the, this gauge bosons and the Higgs is. Yes, just from expanding the d mu phi 1 absolute value squared plus d mu phi 2 absolute value squared. Yes, so these covariant derivatives contain all of the gauge bosons, and you find a relatively simple expression, g squared over 4 h dagger h, and then there will be some numbers here, w mu plus, w mu minus, plus a mu 3, a mu 3. Yeah, so that's the usual thing. It's roughly like the W and the Z, though I didn't include hypercharge here. Yes. Yes. Is it unique? Well, if you are assuming that it's a triplet that is breaking SU3 down to SU2, yes, of course, which SU2 subgroup you are going to get, that's not unique. But the fact that a triplet breaks SU3 down to SU2, yes, that's unique. Yes. Now, one thing that you have to worry about is that, of course, here there are 2 triplets, yes? And in order for you to get the correct symmetry breaking pattern, these have to be aligned with each other, yes? So that's not something that's unique. Yeah, but that's, of course, a question of the UV completion of this theory, yes? But so if I had the VAV here versus there, yes, then that would be different. Yes? Then you would break the gauge group completely. Yes, and that's something you don't want, yes, because then you wouldn't have an SU2 left over. You want an SU2 left over because that's what the W and the Z is supposed to be. Yes, and those should get mass from the Higgs, not from this global symmetry breaking business. Okay. Very good. So again, you just write out these interactions, yes, and you find that there are additional terms here, minus x mu plus x mu minus, yes, and then there's a minus a half y1 mu 0 squared plus y2 mu 0 squared. Okay, minus a mu 8. A mu 8. Okay, so So when you now complete this loop, yes, you will not only have the W and the Z running in the loop, but you will have all these other massive gauge bosons running in the loop, yes. So you will have your X plus minuses, your Y 1, 2, and your A 8 running here, yes. And the important thing is that you get these strange numbers, yes, which if I just wrote you this, it would be looking very weird, yes, that you get those numbers. But of course, we understand that there is a symmetry reason, yes, why it is such that those numbers all add up to 0, yes. And that symmetry reason is exactly the collective breaking of the symmetry, yes, that we have discussed over there. Yes, so you will have, these numbers are going to be showing up here in the, in the interaction vertex. Yes, so you will have 2 here from the W, 1, and then -1, -2, and then they exactly add up to 0. Okay, again, so from this point of view, you may say, oh, it's a miracle or it's something tuned, but we understand that there's a true symmetry reason, yes, that is giving rise to the cancellation of these divergences, yes, and that symmetry reason is what we call the collective symmetry breaking. Okay, so the upshot from all of this is that there are 2 things that you have to remember. Yes, one is that there's something called collective breaking, yes, and that collective breaking is telling you that when you explicitly break the symmetry, in order to keep the good UV properties of the Goldstone boson, you want to do it such that you need at least 2 different interaction terms to be turned on at the same time to explicitly break the symmetry. Okay? And the other thing is that what does the cancellation eventually of the quadratic divergences will be other gauge bosons, other heavy gauge bosons. Yes? So this cancellation is very different than the one Howie Haber is going to be explaining to you tomorrow or next week, yes, where the cancellation of the quadratic divergences due to the gauge bosons is done with gauginos, yes, which would be a fermionic partner. Here you have spin 1 partners of the W and the Z. Yes. So it's the same spin partner. Yes. So a gauge boson loop is cancelled by a gauge boson loop, and it's the underlying global symmetry that is making sure that this cancellation is actually happening. Okay. It only protects the Higgs to 1 loop. Absolutely. Yes. So it doesn't solve the big hierarchy problem. Yes. But the idea is that there is some, strong interaction, some compositeness. Yes. That happens at, let's say, 10 TeV. Yes. And what you're trying to explain is eventually, why is the Higgs actually not at the cutoff scale or one loop at times the cutoff scale, but it's even lower. Yes, it's 1 loop times the F scale. Yes, so that's what will give you 100 GeV. Okay, so so this doesn't solve the full hierarchy problem. This is a 1 loop mechanism. Yes? So it will allow you to get factors of 100. Yes, but it won't allow you to get factors of 10 to the 16. So something else is needed. So there has to be eventually UV completion of this theory. Yeah, so either maybe supersymmetry kicks in at that scale, or it's just a strong dynamics, and that theory will have no more elementary scalars. The one that produced these Goldstone bosons. Yes, so that's sort of the idea. Yes. Yes. Right. Exactly. So the terms that could be quadratically divergent do not depend on the Goldstone boson. Yes. There are terms that depend on the Goldstone boson, but those involve some.
Because that actually corresponds to this.
Exactly. Yes. Right. Any other question? Yes. Very good. So we'll get to that. Yes. So there is already some piece of the Higgs potential generated here. Yes. And there will be also already a loop level quartic introduced here. Okay. Now, I will try to explain to you that in some versions of little Higgs models, you can actually get an even larger quartic. So that's something that I will explain. Yes. Now it's not completely clear whether you need that or not. Okay. But anyway, we'll get to a quartic also. Now this particular model, it turns out it doesn't have a 3-level quartic. Okay. It has a loop-induced quartic, which originally was thought as a bad, feature of the model. Now it turns out that Higgs is actually really light. Yes. So you don't actually need a very light quartic. Yes. So when people didn't know before the LHC started running, when these models were written down, people thought, oh, it's really great. You get a 3-level quartic, and that will give you a Higgs of 400 GeV. Yes. And it turns out the Higgs is not at 300 GeV. Yes. So a loop suppression of the quartic may be welcome. But anyway, we'll discuss, how to get 3-level quartics and which models have and don't have 3-level quartics, today. All right, let me move on to the next obvious question is, how about the fermions? Yes. So what about the fermion sector? Yes. Of course, as we said, numerically, the quadratic divergences from the top are actually the most important ones. Yes. So this is a really important question. Yes. So what you do here is, well, you want to basically just take this model, yes, couple these triplets, yes, to the standard model fermions, such that you still have this collective symmetry breaking pattern. Okay. Well, first of all, there's an SU3 gauge symmetry, so you better enlarge the doublets of SU2 to triplets. Yes. So for example, so I'm just going to write down the top sector. Yes. So the SU2 doublets better be enlarged to SU3 triplets, top, bottom, and capital T. Yes. So it has to be a triplet. Yes. So there will be an additional fermion, yes, that is going to show up here. It will have the quantum numbers of the ordinary top, yes. But now, of course, if I introduce an additional left-handed top, yes, I better make sure that the matter content, the fermionic matter content, actually matches the one in the standard model. So it means that I will also have to have 2 right-handed top quarks. Yes, so there will be 2 right-handed tops. Okay, so I will call these T1 conjugate and T2 conjugate. Okay, and what I'm going to do is I will add a coupling of this triplet with one of the triplets in the theory, with one of the Goldstone triplets. Yes. So this is going to be the same as the top, as an up type quark. Yes. Okay. So the Yukawa interactions will be, there is a lambda 1, so I'm going to couple one of the triplets to this fermionic triplet. Let me call this psi for now. Yes. Times T conjugate 1. Yes. Plus the other phi 2 dagger psi, yes, times T conjugate 2. Okay. So the claim is, okay, so again, these are the 2 separate Goldstone triplets, yes, the ones that contain my Higgs, yes. This psi is, the enlarged fermionic structure, and these are just SU3 singlets. Yes. So the claim is that this is a collective breaking Lagrangian. Yes. Why is that? Well, let's turn lambda 1 off. Yes. Then I will have only lambda 2. Yes. And I could rotate, phi 2 with its own SU3. Yes. And I could rotate psi with the same SU3. And I could rotate phi 1, which at this point doesn't show up in the Yukawa coupling, yes, with a completely different SU3. Yes, so if I turn one of these off, yes, I will have SU3 cross SU3 global symmetry. Yes, if I turn the other one off, then again, then I will rotate this opposite to that. Yes, I will have my SU3, and then phi 2 can have his own SU3. Yes, so the SU3 cross SU3 breaking pattern global symmetry is maintained as long as one of these couplings is absent. Okay, so that will tell you that, yes, question.
So what if you turn on one of Yukawa, the first sector, then gauge coupling with the other sector, so that if you have diagrams, it's lambda 1 and then G2, this cannot have the diagram?
Well, but so you turn on at that point you again turn on two couplings, yes.
But I'm turning
So-
in a cross way.
But you did turn on two couplings, yes.
Yeah, so that I do have a collective symmetry.
It's still collective, yes. I don't know whether, you know, it's not obvious, of course, any two couplings will generate, but you did tell me already you are turning on two couplings, yes. Basically what we are saying is that any single coupling, yes, when you say collective breaking, it means you turn on only one and everything else is turned off.
Right.
Yes, that is the thing that is not supposed to give you, you know, an explicit breaking, yes, and that's still maintained here. Now, it's not obvious that, you know, turning on one of these and one of the gauge interactions will or will not, but it doesn't matter. We know it cannot possibly be quadratically divergent mass for the Higgs, yes, because it's still,
So are lambda 1 and lambda 2 necessarily equal?
they are not necessarily equal. I'm going to take them equal just to simplify our life so that the formulae are simpler, yes, but
So I mean, even the gauge coupling for lambda.
right, the gauge couplings are equal just because, you know, it's a single gauge symmetry. But these two could, in principle, be different. Yeah? So lambda 1 doesn't have to be equal to lambda 2. But, you know, in the formulae that I write, I will take them equal just so that I don't have to write, again, many mixing angles. Yes, but they don't have to be equal. And sometimes you have to play around with those ratios to get a model that is fitting electroweak precision better or things like that. Okay, so very good. So this is the Yukawa coupling, yes, and so you already know that this will be collective. Yes, so we are already halfway done. But let's try to understand what the spectrum of the theory will be. What is the spectrum of the theory? Yes, so after plugging in the expression for phi 1 and phi 2 in terms of the Higgses, yes, what you will find, so I'm going to take again lambda 1 equals lambda 2 equals lambda. That's just because I'm lazy and I don't want to write a lot of formulae, but it doesn't have to be like that. Yes, so in that case, you expand the Yukawa, and what you find is that you get the following Lagrangian I H dagger Q. So this Q is the usual doublet, the usual standard model SU2 doublet times T2 conjugate minus T1 conjugate, yes, plus F times 1 minus H dagger H over 2F squared times the capital T. So that's the additional top that you have added to complete the SU3, yes, T1 conjugate plus T2 conjugate. Okay, very good. So what you find is, yes, that the heavy left-handed guy marries up one combination of the two right-handed guys, yes, so I can call this the capital TC, yes, so this is T1 conjugate plus T2 conjugate over root 2, yes, and the light one, that's the one that is showing up here, yeah, so this is the light, so this is the true right-handed top, is I times T2 conjugate minus T1 conjugate over root 2. Okay, so in this language, what you get is that this whole expression is just a mass for the heavy vector-like tops. So you get heavy vector-like top quarks. Yes, but they still have some non-renormalizable interaction with the Higgs. Yes, so they will get a mass, a vector-like mass, which they are allowed to get, yes, because they are not doublets under SU2. Yes, so they can get a mass with each other without interacting with the Higgs. They will get a correction to their mass from the interaction with the Higgs, and that correction is important, yes, because this is the piece that will actually be canceling the standard model quadratic divergences, plus you get lambda times h q t conjugate plus higher order terms. Okay. So now you can ask again the question, as well, we know already that there will be no quadratic divergences from the point of view of the collectiveness of the breaking. I'm not supposed to write here, yes, so I'm not going to write. Go to the first board again. And so then you're starting to ask, how is the quadratic divergence actually cancelled? How is the quadratic divergence actually cancelled? Yes, so you have your usual standard model contribution from the interaction with the top. Yes, so here you have the top and the doublet. Yes, and here you have your H dagger H. Yes, and then the answer is that, well, what you have is you have an interaction between the heavy vector-like guys and the Higgs also, and there you can just close up the loop. Yes, with an insertion of the mass term. So here you have the lambda t times f insertion, and this interaction here, yes, is coming from that h dagger h over f squared. Yes, and there will be some symmetry factor here, so there's a minus lambda t over f showing up here, and the two diagrams happily cancel each other, at least the quadratically divergent pieces. Okay. So the quadratically divergent pieces are cancelling, and again, just like for the case of the gauge bosons, the cancellation is due to a same spin partner. Yes, so these are called the top partners. So the cancellation is due to the top partners. Yes, so these would be heavy versions of the top. Yes, that are actually vector-like, so they can get a mass, but they can also interact with the Higgs, and their mass will be slightly dependent on the Higgs. Yes, and that slight dependence is what gives you the cancellation. But we understand that that's not a miracle or a tuning, yes, because there is this SU3 cross SU3 global symmetry breaking pattern, that this collective symmetry breaking pattern that is underlying it. Okay, so then, what is the leading diagram, again, that is contributing to the Higgs in the same language as we used for the gauge bosons. Yes, so you can write again that you will need to have, so you have your fermionic loop here, and you will have to insert 4 of these Yukawa interactions. So you can insert here a phi 1, phi 1, phi 2, and phi 2. Yes, and then here you can have a psi, T1 conjugate, and the T2 conjugate running in this loop. And just like before, it will have a similar pattern: lambda to the 4 over 16 pi squared, phi 1 dagger, phi 2 squared times, again, 4 fermionic propagators. So it's log divergent, log lambda squared over mu squared. Okay, and again, it will give you a quadratically a log divergent part to the Higgs mass, which is given by lambda to some power loop factor and f squared. Yes, so this will give you, just like before, lambda to the 4, 16 pi squared, f squared, h dagger h times a log. Okay, yes?
How does the cancellation look like when the lambdas are not equal to 1?
That's a good homework problem. Yes, we know it has to happen. Yes, and I think my guess is that from the point of view of what, because this is here lambda top. Yes, this is the top Yukawa coupling. I think once you express everything in terms of lambda top, I think it will be literally the same, except what is lambda top is not just going to be equal. Yes, it will be lambda 1, lambda 2 over square root of lambda 1 squared plus lambda 2 squared or something like that. Yes. I don't know. I mean, this is what after I go to the basis. Yes. Right. Anyways, it's certainly, we know the symmetry reason it works, and there will be a cancellation there. Yes. Right. So that's an interesting question. Yes. So that's going to be an additional, potentially light, potentially heavy, uncharged Goldstone boson. Yes. And it depends on what you want to do. Sometimes actually, people were playing games. I was playing that game too. That maybe the Higgs can decay to two of these guys. Yes. And then that guy decays to gluons, for example. Then it could modify Higgs physics. Yes, that was really fun before we knew that the Higgs actually looks like the standard model Higgs. Yes, so.
I guess I really more worried about how safe we are from the existence of the light.
Right. So, but it doesn't have to be very light. Yes. So,
Yeah, right.
so it could. It depends on what exactly the symmetry breaking patterns are. So you can make this guy 100 GeV, yes, and then at that point it really is completely safe. That's because it's because it's 100 GeV neutral singlet guy, yes. Now once it's very light, yes, if it has couplings to fermions and then you have to worry, yes. There were not too many constraints when I looked at it back, I don't know, 5-6 years ago, yes. So you could actually, mess around with Higgs physics. Now, of course, you know that the Higgs is decaying mainly as expected in the standard model, so you don't want those channels, yes.
But I guess you can have a low coupling between Higgs and Higgs.
Right. Yes.
Then,
Right. Yes. Yeah. So this could be large, yes. But as long as it's heavy enough that it doesn't decay to the Higgs doesn't decay to it, there's no problem, yes. As I said, if it was light, yes, it had an order 1 coupling, yes, and then the Higgs physics would change, yes. So, all right, very good. So this model is called the simplest little Higgs model. I would like to just briefly mention a few other little Higgs models that people have considered, and mainly just emphasize what the additional features of those models are, yes, and why people are thinking about those. Yes, so one of them, so that was sort of the original and most popular little Higgs model. So that was called the littlest Higgs. And basically, all the ideas are exactly the same. Yeah, so it's just another model with collective symmetry breaking. It's just based on a different symmetry breaking pattern. Yes. So instead of this product group SU3 cross SU3, it's based on just a simple group. Yes. So it's based on the breaking of SU5 to SO5. Okay, so this is your G, and this is your H. Yes. So in this case, there will be more Goldstone bosons. Yes. So in fact, you can count how many Goldstone bosons you will get. So SU5, the generators there are 24 generators of SU5. Yes, and for SO5, yes, that's exactly the antisymmetric. So there are 10 generators. Yeah, so there are 14 Goldstone bosons here, and you can parameterize it, in the nonlinear sigma model language, just like we did before. It's somewhat more complicated. Why? Just because you are taking more complicated groups, and specifically, this symmetry breaking pattern is slightly more complicated because it turns out that to break an SU to an SO, you have to give a VAV to an antisymmetric representation. Okay, so that's what people did. So this was the original model of Ann Nelson, Nima, Andy Cohen, and Ami Katz. Yes, so this is an antisymmetric that gets a VAV. So the way they have written this antisymmetric VAV was in a slightly weird way, but you will understand it in a moment. So they have put the VAVs, spread out in a strange way. So these are unit matrices here, 2 by 2 unit matrix, single unit matrix. And the reason why they did it like this is because what they wanted is you want to gauge some subgroup of this SU5, yes. And what they did is they gauged the two SU2 diagonal the two SU2 subgroups here and there. Okay, so the SU2 cross SU2, and there were also U1s, which I guess I will probably ignore. Cross U1 was gauged. You can sort of understand why you want to double the amount of gauging, yes? Because you need those spin 1 partners, yes? Something has to provide the additional spin 1 partners. If you just gauge SU2 cross U1, yes, there will be no particles that will be present for you to do the cancellation. So they did double, the electroweak group that they have gauged, and actually, so they embedded the SU2 groups over here and over there, and you can see that these VAVs, yes, these are actually bifundamentals under the 2SU2. So those at the same time will already break the SU2 cross SU2 down to SU2 diagonal, and the same thing, the U1 cross U1 down to the U1 diagonal. So you will be ending up with one set of heavy gauge bosons and one set of light gauge bosons, just like, in this other example where, you had the W and the Z light, and you had these 5 additional gauge bosons heavy. Here you will have, the light W and Z, and then you will have a heavy version of a W and Z. Okay, so that's very nice. Yes. Now the thing that is really important here is actually the fact that you have more more Goldstone bosons. Okay, so you have 14 Goldstone bosons, and that seems at the beginning like just an additional annoyance, but it turns out that the presence of these additional Goldstone bosons is what will allow you to actually generate an effective 3-level quartic in the theory. Okay, so the Goldstone, the pion matrix, the Goldstone matrix will look like the following. So you will have 14 of them, and I'm going to write it again in this SU2 cross SU2 structure, the way, that follows the embedding of the two SU2s. Yes, so you will actually have the Higgs. So this will be an SU2 doublet that has the right quantum numbers to be the Higgs, and this Higgs is going to show up in 4 different places. Yes, so you can just check, which ones are the uneaten Goldstone bosons, and here you have H transposed, and here you have H star, the H dagger, and here you will have H star. Yes. Now here you will have a complex triplet. Okay, so here you will have phi 0, phi 0 star, phi plus, phi minus, so it's a complex triplet. And the same fields are going to be showing up here, And then here you will have a real triplet. Something called omega 0, omega plus, omega minus, or minus omega 0. Okay, actually. So the charges of these guys are strange. They are doubly charged and singly charged. It doesn't matter. All right, so this is where you have your 14 Goldstone bosons. And again, first of all, where is the collectiveness of the breaking coming from? Well, let's think about the gauge interactions. Yes. What happens is that if I turn off one of the two SU2s that I have gauged, yes, let's say I turn off the SU2 that I have gauged over here, I still have the SU2 gauged here, then there's actually an accidental SU3 global symmetry that is left over in the theory, yes, which is bigger than the SU2 that I have gauged. Yes, so turning off one of the SU2s, yes, there will be, let's say I turn off the SU2 that I have gauged down in this lower right corner, yes, then this whole SU3 up here, yes, is going to be a global symmetry. And SU3 global symmetry will be there. Yes. And the important thing is that the Higgs will transform under that SU3 global symmetry. It will have the shift symmetry under that unbroken SU3 global symmetry. So the Higgs will be protected. Okay. If I do the opposite, yes, if I now turn off this SU2, then you will have an SU3 showing up down in this lower right corner. Yes. And again, the shift symmetry corresponding to that SU3 is going to protect the Higgs. Yes. So it's again the same game. You need both SU2s to be gauged in order for you to cancel, to generate a potential that will depend on the Higgses. Yes, so that will mean that the quadratic divergences will have to cancel. Okay, so you will be able to say exactly the same story that you had for the simplest little Higgs. Yes, for the cancellation of the quadratic divergences from the I'm sorry? There's probably a singlet though. Is there a singlet? I don't remember anymore. 4 plus 6. Yeah, there is another one, yes. Okay, so the cancellation of the quadratic divergence will be again written in terms of these heavy gauge bosons. There will be a contribution with the plus g squared with the light standard model gauge bosons, and then there will be a heavy version of those gauge bosons, and the symmetry will dictate its coupling. As its coupling is, you can actually work it out very easily, is going to be a minus g squared with the heavy gauge bosons. Okay, so there will be a cancellation. Again, the cancellation is with the same spin particles, so these are called the spin 1 partners of the simplest little Higgs model, and you know the story goes just like it did before. You can do the fermion sector also. It's very similar to the case of the simplest little Higgs, so I'm not going to bother writing that down. So I wrote it in the notes, but it doesn't. No, there's really nothing novel here. There's one novel aspect compared to the simplest little Higgs, and that's the case of the quartic. Okay, so the novel part here is the quartic, namely the fact that in the case for the simplest little Higgs, the quartic was loop induced, and in this case for this littlest Higgs model, this SU5 mod SO5 model, yes, the quartic will be 3-level. And that looks very weird, yes? How could it possibly be a 3-level quartic, yes? I mean, how could, you know, I mean, there is no explicit breaking here that is going to give rise to that. So that was something that that for me was hard to understand. But the important part here is that you actually have these additional Goldstone bosons. So the presence of the additional Goldstone bosons are the thing that will allow you to truly generate a 3-level quartic. Presence of the additional Goldstone bosons will lead to the quartic. Okay, so how does this lead to the quartic? Well, so you go ahead and you start calculating the quadratically divergent part of the potential. Okay. So calculate the Coleman Weinberg potential, yes, usual thing, lambda squared over 16 pi squared times the trace of the gauge boson mass matrix as a function of the Goldstone bosons. Yes, that's the leading piece in the Coleman Weinberg potential. You take your pion field, yes, it's you write the gauge boson masses as a function of the sigma. Okay, it doesn't matter. What you will find is, yes, the quadratically divergent part, yes, from the gauge bosons, yes, will be, so there's some order 1 coefficient because you don't truly know what this quadratic divergence is. Yes, it has a counter term, yes, is a g1 squared plus g2 squared. No, this should be g1 prime squared. This should be the u1. Okay, and there's an f squared, and you will get a piece that is corresponding to that complex triplet phi ij, yes, plus you will get another piece that is now containing the Higgsis hi hj plus hj hi absolute value squared. Okay, so this is the piece coming from one of the SU2. So the G1 is the gauge coupling of the first SU2. The G1 prime is the gauge coupling of the first U1. And you get a piece, yes, that has a peculiar structure. Yes. Well, first of all, there is a quadratic divergence for the other Goldstone boson. Yes, because the phi that is in the corner, yes, that actually is not protected by the collective symmetry breaking. Yes. So that Goldstone boson will pick up a mass that is bigger than the one for the Higgs. Yes. So it's the Higgs picks up a mass that is of the order f over loop factor. Yes. And the phi picks up a mass that is just f. Yes, which is coming from a lambda over loop factor. Yes. So this phi is going to be quadratically divergent, and it actually will have cubic interactions, yes, with the Higgs itself. Okay. Now, if this was all there was, yes, when I integrate out phi, I would integrate out every interaction with the H itself also. But this is not all, because there's a second term coming from the second SU2 group, yes, and that will have a very similar structure, except there will be some slight crucial differences. There will be a different sign showing up. Okay, so there will be another piece, yes, A times G2 squared plus G2 prime squared, yes, F squared, again exactly the same thing, phi ij minus I over 4f hi hj plus hj hi absolute value squared. Okay, so this guy is relatively heavy. Yes, so if the Higgs is 100 GeV, the phi is going to be roughly of the order of a TeV. Yes, so I should integrate out this additional Goldstone boson in order to get the true effective potential for the Higgs. If I had only one of these SU2s turned on, yes, then when I integrate out the phi, all this other interaction term is going to be integrated out also. Yes, but I have two of them. Yes, and once, because there is a slightly different way they are coupling to each other, once I integrate out the phi, yes, these cubic interactions between the phi and the H will actually lead to a true non-vanishing remaining 3-level quartic for the theory. Okay, so after integrating out phi, there will be a 3-level quartic for H. Okay, so this is what is called a collective 3-level quartic, yes, and this can only happen if you have additional Goldstone bosons present in the theory. Yes, so it's a sort of a a very subtle effect. Yes, it's saying that, well, there's another guy. It has these cubic interactions with the Higgs. Yes, there is still a collective protection for each cubic interaction on its own. Yes, but once I take the two together, there will be a leftover effect for the Higgs, and that will actually generate a true non-vanishing quartic for the theory. Okay. Yes.
If I turn off either of the SU2s, they should disappear.
They should disappear. So this is why it is a collective quartic. Okay. So the form of the quartic will be, so this is the quartic, and let me just write it down: G1 squared plus G1 prime squared times G2 squared plus G2 prime squared. Yes, divided by some. I think this is the sum of all the couplings. Yes, exactly. So this has this structure, yes, that if I turn off one of the SU2 cross U1s, it goes to 0. If I turn off the other SU2 cross U1, it goes to 0. But when both of them are turned on, yes, this is a collective 3-level quartic. Yeah, if you turn off because there's the U1 also, yes.
I don't see the SU3s breaking when the U1 is alone turned on.
Well, the U1 is embedded in a strange way. The U1 is embedded. I didn't write it down. Okay, the U1 is, where is it? The U1 is embedded. So Y1 is 3 minus 2 minus 2 minus 2. Okay. So I think from this you understand it. All right. So again, this is a subtle effect, and this can give you a 3-level quartic. So how does then the potential, the actual Higgs potential, look like for these little Higgs models? So I will get a possibly log divergent, but not quadratically divergent mass term, yes. So I will get something of the order of G standard model squared, and here I'm going to put in the biggest contribution, which is coming from the fermionic loops over 16 pi squared, yes, times H absolute value squared. So this is going to be the possibly log, and there could be another log here, as there could be a log lambda over mt. Okay, so this will be the collectively protected one loop, but it's proportional to the mass of the little partners, or the spin 1/2 partners, or the spin 1 partners. Yes. So this is a relatively small mass term. Yes. Plus there will be a term which is of the order of G standard model times Higgs to the 4th. Okay, so this is roughly how the actual Higgs potential of the little Higgs model will look like. Yes, of the little Higgs model where there is a quartic. Yes, in some cases the quartic is loop. Yes, you die.
Whenever you say 3-level,
there's no loop factor. That's what it means. Otherwise, it came from loops. Yes. So it's a very subtle effect because it came from the quadratically divergent loop, yes, that generated, both the mass and the cubic, and after integrating out, but the loop factors drop out after integrating out, yes. Okay, so that's the potential, and where will the VAV be? Yes, well, so that this is something of the order of f. Yes, so this is something order of G squared f squared divided by 16 pi squared. Yes, and here you have a G squared. So the Higgs VAV will be of the order of f over 4 pi. Yes, if you take this potential, minimize it, yes, this is something like f over 4 pi squared roughly, and this is just order 1. Yes, so the Higgs wave will be of the order of f over 4 pi. Okay, so this will be a truly, completely natural electroweak symmetry breaking. In the sense that if this is 1 TeV, yes, then this wave is going to be naturally suppressed by, roughly a loop factor, yes, so it's going to be smaller, so V over F, yes, is naturally smaller than 1. Okay. Now, of course, this is very nice, but, the fact that we did get this additional suppression relied on the fact that I have an order 1 quartic. Yes. Now, this order 1 quartic, again, before we knew what the mass of the Higgs was something fantastic, yes, because it allowed you to get this, this natural Higgs potential, yes. But the quartic also sets the mass of the Higgs, yes, and the mass of the Higgs is, root 2 lambda times V, yes, and if for this to be 125 GeV, yes, it turns out the lambda should be more like 1 over 8, yes. So now is this a tree level or is this a loop? Yes, well, I don't know. It doesn't look 1. Of course, it also doesn't look like 1 over 16 pi squared. So, but the upshot is if you put 1 here, yes, you will get something that is a little bit too heavy. Yes. So if you put the quartic to be truly 1, yes, well, you will get, I don't know, root 8 times, what the mass of the Higgs actually should be. Yes, so you will get something like 300 GeV. Okay, so this quartic shouldn't truly be 1. Yes, it should be something smaller, somewhat smaller. But then, of course, once you start making this quartic smaller, that quartic is what made the wave, the ratio of the wave to be the right one. Yes, so then you have to start worrying that you still get the right minimum of the potential. Okay, very good. So that's the so-called simplest, the littlest Higgs. Now let me move on to another kind of model, which is again along the same direction, which is called the minimal composite Higgs model. And I will try to explain to you what the differences are. Yes. From the top partners. Yes, exactly. Yeah, so it's coming from writing down the full, and that's what gives you something negative. Yes, and there is also a gauge boson contribution, but it's smaller, which is positive. Exactly. Right. Very good. So minimal composite Higgs. So what is the difference in these models? Because you often hear these little Higgs models, and then other people like to talk about the composite Higgs or minimal composite Higgs. Well, it's basically just another model, pseudo-Goldstone Higgs model of the sort that we have been talking about. Yes, there is one important additional ingredient here that it incorporates custodial symmetry. And that's pretty important, because if you go ahead and try to calculate the electroweak precision corrections from, for example, this littlest Higgs model, you find that actually, those electroweak precision corrections are not that small, because there are tree-level contributions, for example, to the T parameter. Yes, and this F that you want to be 1 TeV, yes, turns out that it wants to be more like 3 or 4 TeV. Yes, and that will start again, introducing hierarchy, and that's not so good. I mean, there are ways to fix it even within the littlest Higgs, but this is sort of the most natural way to go. Basically, the idea is that the most sensitive electroweak precision observable is called the T parameter, and there is a symmetry that can set that T parameter to 0. Okay, so the T parameter can be set to 0. And unfortunately, I don't have time to explain what all of these electroweak precision observables are. I could give a whole series of lectures on that. Sometimes I have done that, but since I'm out of time, I'm not going to be explaining it exactly. But the important thing is that if you take an SU2 left cross SU2 right symmetry, yes, so this is what is called the custodial symmetry, and that broken to SU2 diagonal, yes, that global symmetry breaking pattern is the right one that actually happens in the standard model. Yes, and that's something that is important for you to understand, that the Higgs potential in the standard model actually has a bigger global symmetry than the gauge symmetry of the standard model, because the Higgs you can write in the standard model as H1 plus I H2, H3 plus I H4, and every term in the Higgs potential depends on this combination H dagger H, yes, which you can write as H1 squared plus H2 squared plus H3 squared plus H4 squared. So this you can see actually as an expression that has a bigger global symmetry. It has a 4-dimensional Euclidean rotational symmetry, yes, which is bigger than just the SU2 rotations of the standard model. Yes, so this actually has an SO4 global symmetry. So the standard model has an SO4 global symmetry. Yes. Now this pattern is also familiar to us from yesterday, yes, because this is the kind of pattern that happens in QCD. Yes, because in QCD what you have is SU3 left cross SU3 right broken to the diagonal, yes. So if you restrict it just to the SU2 subgroup, as you have SU2 left cross SU2 right broken to the diagonal. Yes. And this is the relation I mentioned to you, that at that point it looked miraculous that QCD gave you exactly the same mass ratio between the W and the Z, yes, as you get from the Higgs. Well, it's because it is based on the same symmetry breaking pattern. Okay, so the idea of this minimal composite Higgs model is to say, well, let me try to make a model, yes, that actually has an explicit SO4 global symmetry, yes, that is not broken by the strong dynamics. So an SO4 global symmetry is left untouched by the global by the strong dynamics, yes. So that will ensure that the strong dynamics does not have any contributions to the T parameter. Yes. Of course, this is not an exact symmetry, so it will be broken by gauging SU2 cross U1, but that's happening in the standard model too. So you will just get the same corrections to the T parameter as in the standard model. Okay, so that was the main idea. So how to do that? Well, actually it turns out that it's really simple, because if you take an SO5 global symmetry and break it down to an SO4 global symmetry, yes, well, how many Goldstone bosons are you going to get? Well, it's exactly 4, yes. And what representation of SO4 are they going to be? They are going to be in F4 of SO4, just like this beast here, yes. So this breaking, yes, gives you the minimal number of Goldstones, yes, which is just exactly what you need for the Higgs, yes. But it also ensures that custodial symmetry is completely unbroken. Yes, so custodial symmetry is preserved. Okay, so basically you are trying to build. You're trying to build a Goldstone model based on this SO5 to SO4 breaking. The first comment is you have the minimum number of Goldstones. Yes, so this idea about a collective quartic is certainly not going to work here. Yes, so this will not have a 3-level quartic. So it means that both the quartic and the Higgs mass parameter will be loop suppressed. Yes? So how will the Higgs potential look like in this model? Yes. Well, where did I write it for the? Yes. So let me write it, below here. Yes. So in this case, both the quartic and the quadratic terms will be loop suppressed.
Will you always get the proper sign? Maybe a negative mass to
Well, if you of course, right now you can't tell, yes, because I didn't quite tell you what the partners are, yes. So when people talk about the minimal composite Higgs, they have sort of two versions in mind, yes. One is sort of just a generic model that has this symmetry breaking pattern, but they don't tell you where, what the partners are, yes. Then of course you can't tell, yes, and it depends on what the partners exactly do. Now, tomorrow I'm going to be talking to you about extra-dimensional versions of these models, and there this potential is calculable, yes. And it turns out that there are regions where you get the right Higgs potential, yes. Not always, but often you get the right Higgs potential. But again, the thing that I want to emphasize here is that for this minimal composite Higgs, yes, the Higgs potential will be something of the form. So there is G standard model squared times F squared over 16 pi squared. Yes, and then there is some parameter A here, and then there is a quartic with some parameter G standard model squared over 16 pi squared h to the 4. Yes, and now you have a problem. Yes, because both the quartic and the mass parameter are loop suppressed. Yes, so when you minimize this potential, you want to get F to be of the order of V. Yes, you minimize this, and this is the only, both of these terms are of the same order. That's the only mass parameter. So on the other hand, of course, you need V over F to be much less than 1. Yes, so there will be, so these kind of composite Higgs models that don't have a 3-level quartic, they always have sort of an irremovable tuning. Yes, the tuning, it turns out, will go as V over F squared to produce the right Higgs web. Yes. So now how small does this V over F have to be? Well, it turns out that maybe something of the order of a quarter is enough. Yes, V is 246 GeV, F is a TeV. So a tuning of something of the order of 10% or 5%, but that's something that is basically irremovable from these theories. Okay. Yes, so maybe you can do that, yes. Right. This, I'm talking specifically about this model, which is a very generic one, and many other models, like the simplest little Higgs, also doesn't have a quartic, yes. I mean, a 3-level quartic. So I just want to emphasize that that's the main difference, yes, at least from the point of view of the phenomenology. And there was one more thing I wanted to say. Yes, that's kind of important. Yes, so when you write down how the Higgs potential will actually look like, yes, how the coupling of the Higgs to the gauge bosons will look like. Yes. What you will find is that because, of course, the Higgs is a Goldstone, yes, the actual coupling is going to be, it's coming from an explicit breaking, yes, but it has to involve the trigonometric functions of the Higgs, yes. So the actual coupling between the Higgs and the gauge bosons will be through this combination, F squared sine squared H over F. Okay, and here you get your usual B mu nu, B mu, B nu, whatever, plus W mu 3, W nu 3, yes, whatever, doesn't matter, yes, times G mu nu minus Q mu over Q squared, yes. The important thing is, yes, that it's not H squared that is going to show up, yes, but this trigonometric function, yes. So the VAV actually has to be identified with this combination, yes. So V has to be identified with F times sine H over F, yes. And then what you're supposed to do is, yes, you're supposed to expand this function around its VAV, yes. And how will that look like? Yes, so the expression will look like, you know, once you expand this, it will have the usual thing, F squared sine squared H VAV over F, yes, plus 2 sine H over F cosine H over F times H over F, yes, plus other terms, doesn't matter, yes. So the important thing is that this is not going to be exactly equal to V times H. Yes. The fact that you have this trigonometric function showing up, yes, which is a consequence of the Higgs being a Goldstone, yes, will slightly modify the coupling of the Higgs to the gauge bosons. Yes. And so the way you can write this is, the way this is usually parameterized is, you write this is V squared, of course, and then here you get 2V times root 1 minus psi times H plus, if you write out the other terms, 1 minus 2 psi H squared, etc. And then this is the combination that is going to couple to the B mu, etc. Okay, so there will be this deviation. Yeah, so in the standard model, this would just be 2V. Yes, but here you get this deviation where psi is V squared over F squared. Okay, so what? And this is, of course, not just a property of the minimal composite Higgs. This is a property of all the other little Higgses, yes, but somehow it's always emphasized in this particular model, so I'm doing it here. So this model, one prediction, irrespective of what the top partner and the gauge partners are, is that it will give you small deviations in the coupling of the Higgs to the gauge bosons, yes. And so if we don't see any of that, yes, then we can sort of start excluding the the compositeness of the Higgs. Right now, the bound on this parameter is not that, the precision of the of the Higgs couplings is not that large yet. So the bound is not very severe. But at some point you will expect that you will start putting bounds on F to be multi-TV, and then you will again start questioning whether the Higgs is actually composite or not. I think there could be a numerical factor here that depends on what the particular group is, what the particular coset structure is. I thought the sign is always the same as far as I remember. Yes. I thought there could be a numerical, there could be some group theory factor showing up here depending on the on which coset you have. But I thought for this particular coupling, the sign is always is always making it smaller. Yes. So. Right, but I guess what he's asking is, could it be another trigonometric function? Yes. As far as I know, it's always less than 1, but I don't know if there is a proof that tells you. All right, so I'm gonna finish here. I didn't get to partial compositeness, so if you guys want to ask me and girls want to ask me during the discussion, I can say a few words about partial compositeness. So that's sort of a way of getting the flavor structure out of these composite Higgs theories. And tomorrow we'll have to move on to extra dimensions and particular warped extra dimensions, and hopefully discuss ADS-CFT and how to connect all of these composite Higgs models to the extra dimensional warped versions, and how to get the Higgs out as a fifth component of the gauge field. All right, let's stop here. Before we break, we'll come back. We have the such and such
Earlier in the week we had Sally and who's besides Csaba? Who were the two people on the first day? You and you. So. No, it was. So we have to divide the room. I just sorry, I told out. We did it like this. We were like this time, and people in the back of the room go down to. And we'll resume at a quarter till, and I'll make sure that the two teachers know where they're going.
Good.